Afternoon. My name is Stephen Vitale, and I'm here presenting on the Insight platform for professional development hours. Insight is a leader in the authoring of professional hour development courses for continuing education for engineers and other professionals. I'm in, Let me tell you a little bit about myself. I'm in the gas industry. In another less than 2 weeks will be 53 years. I have a PhD in mechanical engineering. I have a master's degree in mechanical engineering, a bachelor's degree in mechanical engineering, and a master's degree in civil engineering. Been licensed in 6 states as a professional engineer and have a host of experiences across many different petrochemical plants, mostly LNG plants, liquefied natural gas plants, and within the gas industry, both in distribution and transmission work. My real passion is to enhance safety and reliability of LNG facilities. Let me give you a little bit of background. When I started my career back in 72, in the second year of my career, I remember calling my boss's home. He was doing a Sunday job, and I had asked him to stop off at one of my jobs where I was running a hydro test. My hydro test was a 250-pound hydro test, and it was losing pressure every day. The piping was buried in groundwater, and it was a hydro test. So as the groundwater got colder, so did the water in the piping get colder, and my pressure was going down, spiraling down every day about 1 to 2 pounds. And I just wanted to check that if one point the groundwater was raised in temperature, I could go out there, pull the chart, and say, here's the correct test. The test has been satisfied. However, that Sunday, he was working a Sunday job. I called his home, and his wife was frantic. He said, Steve, there's been an explosion. And I said, look, don't worry. I'm sure there's been an explosion. I can't get hold of the dispatcher. I don't know if Frank was involved. I said, look, I'm fine. I'm sure everything's fine. I'll drive to the job and have him call you back. I drove to the job, and while I was en route to the job, his name was mentioned over the radio as being deceased. And when I got to the job, they said he was taken to the hospital. I went to the hospital. They told me, we can't speak to you because you're not next to kin. Well, he died on that job, and we'll go over that accident and what happened in that accident. Within 6 months of that, I got a call that from one of the workers in the field, and I picked up the phone and said, Steve, there's been an explosion on the job. 2 men were killed. And we'll go over that job as well, see what happened. But this is one of the reasons that early on in my career, I got a passion for safety and reliability. And I've ended up most of my career always been investigating safety issues that have occurred, and they always have a single theme, and that is engage the brain before you take your foot off the clutch. And that single theme is expect the unexpected for engaging the brain and prepare properly, follow procedures, follow MOC, follow lockout, tag out, and so on. We'll talk about many of those issues. But first, and some of these safety moments will be strictly technical in nature, not necessarily an actual accident. Let's start off talking about uh, ruptures, gas pipeline ruptures. If you look over here, you see a gas pipeline rupture that occurred in San Antonio. This was not San Antonio, San Bruno, California. And you see what happened. The pipe actually ripped apart. It didn't puncture a hole, it ripped apart, blew out of the ground. Here's another rupture that occurred, and this occurred in Milford, Pennsylvania. In fact, I was living in Milford, Pennsylvania at the time when this occurred. And if you notice, what's unique about both of these is that there's a piece of pipe missing. So what happens in a rupture is that a pipe blows out of the ground. It literally ruptures to the point where there's a section of pipe missing, and you have gas flowing into the break from 2 different locations. Now, remember when I told you about not engaging the brain before your actions? One of the things I forgot to tell you is what I did early on. Also, right after those two accidents happened, I went across a a location where a gas main was ripped out of the ground. It was only 2 inch in diameter, and the gas was blowing. I jumped into the opening, wrapped a rag around a stick, stuffed the stick into the pipe. Immediately, the gas pressure built up behind the stick, and the rag, the stick, and myself got thrown across the trench, and I climbed out. Now, this is where I say engage the brain before taking your foot off the clutch. Before I jumped into that trench, there was nobody in the trench. There was no risk to property or person. Once I jumped into that trench, I not only put myself at risk, but I put my company at great liability. I could have said, "Is there a hazard? Yeah, gas is blowing. So what? What if it catches ignition? So what? We have a big fire. It's embarrassing, but we have a big fire in the area, but there's no houses and no people in jeopardy. We could dug a hole, closed off the pipe, and the flame would go out, and all is finished." So when you look at as we go through these, keep in mind actions that are taken by people that they jump in and not think before they jump in. Now, I mentioned this is a rupture, and the reason why I'm showing these is because these could have been prevented. In this case, this rupture occurred. There was a vintage pipe that should have been captured in their surveys as being susceptible to failure. And in this case, they had repigged this line and they were bringing it up to pressure when this ruptured. So these things could have been captured ahead of time. These failure mechanisms could have happened ahead of time. Now let's do a little experiment here. I'm going to take a balloon, and the first thing I'm going to do is see if I can get a little static electricity on this balloon. And this has nothing to do with and you notice the balloon was sticking to my hand? Well, that is static electricity. And the reason why I bring that up is because it's a source of ignition. And I just want to bring that up as a point of information, not to do with the presentation I want to show you. See this pin? This is maybe you can't see the pin. There it is. It's a backhoe bucket. And the backhoe bucket punches into the balloon, and look what happens. Nothing. I have a leak, and I can feel the air blowing out of this balloon. So let me take a different balloon now, and I now get this backhoe bucket. What happened? Well, it blew up. One ruptured, one leaked. Why did one leak and one rupture? Well, is it because the balloon is yellow? No. Is it because the balloon is highly stressed walls? Yes. Is it because the air molecules are crushing into the walls of the balloon, causing pressure? Well, that pressure causes the stress. The correct answer is the stress. Here's the balloon with the pinhole in it, and it did not rupture. So the question is, what caused the rupture? Well, GTI, Gas Technology Institute, hired Battelle Laboratories to do an analysis and experiments and a research study on why pipelines rupture and why some leak. And what they found was that at above 25% of SMICE, and I'll define SMICE in a moment, above 25% of SMICE, pipes will rupture or leak, dependent upon conditions, will rupture or leak if they're hit by a backhoe or by some mechanical force mechanism, perhaps a boring machine or something like that. But they found that below 25% SMICE, they will not rupture. They will only leak. So that's the balloon, which got the backhoe bucket hit and it only leaked. So based on that information, distribution mains, which are low pressure mains, are defined as gas mains that operate under 20% of SMICE. And mains that operate above 20% of SMICE are called transmission mains. Now, how many mains are there in the United States? What's the length of these mains? Transmission mains in the United States is about 300,000 miles. Distribution mains is about 1.3 million miles of distribution mains. Distribution mains will not rupture, but they can be totally pulled out of the ground if a backhoe grabs it and rips it out of the ground, but it will not rupture if it's impacted by a backhoe or by some piece of mechanical equipment. They also found that mains will either rupture or leak depending upon the type of defect they have. If they have a defect in the main, sort of one very common type of defect would be a corrosion defect. What is SMICE? That's specified minimum yield strength. It's when the piping is made, what is the specified minimum yield strength? So if I say a X60 pipe, we know that it can withstand 60,000 pounds of force pulling it apart, as would be a hoop stress, pulling it apart or some other stress. And when you let go, it goes back to its original position. It's within the elastic range. And now you can take 20 samples out of a pipe. Maybe one comes out 61, 62, 65, but it has a minimum. That's what the specified minimum yield strength is. Happens to be 60,000 pounds per square inch for that steel. So they found that if it's over 25% of SMICE, it could rupture or could leak. If it's over 30% of SMICE, it could rupture or leak due to corrosion. But over 25%, between that 25 and 30, only mechanical damage was given as the reasoning for a rupture to occur. That doesn't mean a rupture will always occur. Sometimes you'll have a corrosion hole. You're operating at 35% SMICE, and it just leaks. It depends on the shape of the defect. And why does it depend on the shape of the defect? Well, think about this. This is a piece of paper. It's nice and strong. But if you put a little defect in that piece of paper, it rips real easy because the crack becomes a stress concentrator. So at high levels of stress, when you get that stress at a crack or at a rip or a little tear or puncture, that rips right around the pipe, releasing the pipe from the ground, rips down the pipe, and a whole section of pipe can get blown out of the ground. Now, what's happened is we then say, okay, well, how much of a percent SMICE are we going to allow pipelines to operate at? And what DOT did was they looked at the population near the piping, and they made classifications for class locations. So a class 1 pipe is as shown here. Here's a class 1 pipe, and they're allowed to operate up to 72% of SMICE. Now, where do you think class 1 is? Or any piping that's underwater, where there's no houses, no buildings, no people, no property to be damaged. Any piping that's running through a forest where there's no buildings or property to be or people to be harmed. Then you have 60% of SMICE. That's class 2 area. Well, that's an area where you might have 10 up to 10, no, I'm sorry, up between 11 and 46 people, 45 people, between 11 and 45 residences within the zone area, and I'll explain the zone area in a moment. And you might say, well, what about a class 1 that has only one person there? Well, you're allowed to have within that zone area up to 10 locations or 10 homes within that zone area. What's the zone area? It's 220 feet, 220 yards, that's 660 feet on each side of the piping and a mile long. So if you took a glass window that was mile long and 620 feet in each direction and move that over the pipeline and then count the number of houses that are within that imaginary zone that you're carrying. And then when it hits 10 or more, it becomes a class 2. As long as it stays below 10, it's a class 1. What about if it's 46? Well, 46 and higher becomes a class 3. 46 and higher can also be, I'm sorry, let me get back there. 46 and higher can also be a place where there's public assembly taking place. Public assembly of 50 or more people within the area of actually it's within 300 feet of the pipe. Well, that section of pipe has to be a class 3. And what's a class 4? Well, a class 4 would be where the predominance is 4-story buildings. So middle of Manhattan, it's going to be a class 4. Now, middle of Manhattan, you can operate up to 40% SMICE legally. But many utilities decide, well, in the middle of Manhattan, do I really want to have a rupture occur if it gets hit with a backhoe? No. So they may opt or choose to operate at 23 or 22% of SMICE, something below 25, to not run the risk of having a rupture occur if that main were to get hit. Now, that's true for pretty much older mains where the integrity of the main is somewhat not certain, but maybe a main that was installed last year, well, they may operate at near 40% because they have high confidence in the integrity of that gas main. So these are the amounts that are allowable for the different zoned areas. However, waivers are available in some cases where a specific hardship may occur to the operator of that pipeline. So there are waivers available, and not them saying you should get waivers, but just as a piece of information. Let's take a look at the effects of I got multiple screens open because I have multiple pieces of information. And one of them talks about what does the software say and how do they select how much heat radiation is going to come off of a pipeline. DOT, Department of Transportation, has defined what's called a PIR, potential impact radius. And the PIR is based on a formula 0.69 times the pressure the pipeline's operating at times its diameter squared. And it comes up with this number, and it's number of feet from the pipeline, which is considered the potential impact radius. And does that mean that if you're standing 1 foot outside the potential impact radius, you're safe? Not at all. If you're on the line of, let's say it's 500 feet, if you're 500 feet away from a break, it only looks at the radiant energy that comes off of a vertical flame. Now, if you remember when you looked at, and I'm going to go back and take a look at that, this pipeline here, you think that's pointing the flame vertically upward? No, it's pointing it way to the side because that gas is coming out here way to the side. Plus, also look at what happens here. When this blew out of the ground, do you think it's blowing out at a steady state? No, the initial blast is much greater. So does the PIR, the potential impact radius, really define the area of consequence? No, and here's why. You know what I forgot to do? I forgot to set my timer, so I'm going to have to keep moving along, and I just set the timer. So what's happened is the potential impact radius is going to be just a number that's used for code delineation, because once in a PIR, there's limitations associated with building within a PIR. There's also what's called a hazardous area, and that's defined as any type 1 or type 2 area is considered a high hazard area. Any type 3 or type 4 area, actually type 3 or type 4 area would be a high hazard area. And type 1 and type 2 that has identified sites in it, that unidentified sites are listed as what they're defined as in the code. Well, let's move on. This is what happens in an urban area, and this is what happened in the San Antonio area. Next, I'm going to look at, and I don't know why it's not showing here, stratification. This slide is not showing properly. There it is. Okay, safety moment number 2 is stratification. What is stratification? Stratification is when layers of LNG lay on top of each other. Like here you see a layer of LNG. This is heavy LNG. Typically when I ask a class, where would you put heavy LNG if you had a dense LNG come into your plant and you need to store it and you have light LNG in your tank? 90, no, maybe 75% of the times, students or learners will say you put it on the bottom. You always put the heavy stuff on the bottom. Just the opposite. Put the heavy stuff on top. Why? So that the heavy LNG mixes through the light LNG, and then you have a homogeneous mixture. If you put heavy LNG on the bottom, let's take a look at what happens. It stays on the bottom. And what's so bad about that? Well, it stays and it circulates within itself like this here. Why does it circulate like this? You have heat coming in here, makes it light, buoyant, goes up and goes around, and it can't push through this very light layer of LNG. So it gets, what happens as it stays and circulates in here? There's no cooling taking place, so it gets hotter and hotter and hotter. What happens to the top layer? Well, it evaporates on the top, so it stays cold, stays at its very cold temperature. So let's say this is minus 256 degrees Fahrenheit, and this becomes this bottom layer goes from minus 256, minus 254, minus 250, minus 248, minus 246. And what's happening as it's getting warmer? It's expanding. And what's happening to its density? It's getting less and less. So the bottom layer is getting less and less dense. And look here, I put numerical values on it until eventually it rapidly mixes or flips. No one knows whether it really flips or rapidly mixes, but we know that a rollover has occurred. And when a rollover occurs, that warm bottom LNG sees the top pressure of the tank, which is a very low pressure for that temperature, and it boils up very rapidly. How rapidly? There's been two major incidents, and I've been called out to one. Wasn't a major incident, but it was a significant incident, and consulted on what happened at that location. And what happens is when it starts to boil off, it can achieve boil off rates in excess of 180 times the normal boil off rate of an LNG tank. What are the relief valves set for on a relief tank, on a LNG tank? Well, by code, they're set for only 60 times your normal boil off rate. So if your normal boil off rate is, let's say, 1, and your relief valves are set for 60, and now you get 180 times that boil off rate, what happens is your relief valves become overtaxed. They can't relieve enough pressure. Your tank overpressurizes. It's a very unhealthy situation. Why does LNG stratify? There's two basic reasons. One is fill-induced stratification, as I just showed you. We put a heavy LNG on top of a light LNG. The same could happen if you put a light LNG on top of a heavy LNG. And another mechanism, which we won't have time to really discuss, is that nitrogen can cause LNG to auto-stratify. And there's another form of nitrogen stratification that where the bottom layer is due to fill induced, but the bottom layer has nitrogen, and all of a sudden it starts boiling before it even gets lighter than the top layer. Well, think about it. If it starts boiling, it's got bubbles inside of it. It's going to puncture through that top layer and start a rollover. So there are two ways to start a rollover: fill-induced stratification and nitrogen-induced stratification. But before a rollover, you have stratification. That's key to know. This is a normal tank, and this is how a normal tank circulates. You got warm LNG. This becomes slightly warmer, and therefore it becomes buoyant, rises to the top, evaporates, becomes more dense, drops to the bottom, gets warmer, 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 comes up, evaporates. That's the way a normal tank operates. And this is the way that stratified tank operates. And as you see here, you have this high amount of mixing. So I was called out to a location where the plant had a rollover condition. This plant happened to at the time have 5 tanks, and they couldn't understand what happened. The relief valves vented, and they called me, and I looked at the temperature and density profiles, and I was able to say, yep, here's what happened. You had a rollover. Now, what happened there in that particular case is the superintendent knew that he had a stratification, so he pumped out the bottom layer, and that's how you get rid of a stratification. You pump out the bottom layer to the top of another tank. And this way it goes through, assuming that the density of that other tank is lighter than this bottom layer, it goes through that top layer and it mixes. But this plant had been so much a mindset, you always bottom fill, because bottom fill produces less boil off. You always bottom fill. So he took the heavy layer, took it from one tank, put it underneath another tank. All he did was transfer the stratification from one tank to another, and immediately thereafter, they had the rollover. The next safety moment we're going to talk about is LNG or pipes can levy. LNG tanks or pipes can levy. Now, there's when we think about Blevy, we typically think about a propane tank and a fire because that's most typical types of Blevy. Propane tank and a fire. And what happens in that case, a propane tank may be on fire, and this upper portion of the tank gets heated by the fire. The bottom portion doesn't get heated because it has liquid in it. So the liquid is drawing that heat away very quickly. The top of it goes above 800 degrees Fahrenheit, becomes weakened, eventually blows out, and all of this high pressure liquid that's at saturation temperature, because it's boiling, now blows out of here and atomizes into a big vapor cloud. Now, what happens? Well, let's say this liquid was water. Well, all you have is a Blevy, which is a boiling expanding liquid vapor explosion. But if that liquid happens to be propane, you have a secondary explosion of this very well mixed atomized air gas mixture, which are a boom, boom. So you have a very large explosion called a Blevy. How else can you get a Blevy? Well, you can have, let's say, an LNG pipe that has closed valve, closed valve, and inadvertently, I say inadvertently because it should never happen, a closed valve between this pipe and this relief valve. Now, this is typically called a TESV, thermal expansion safety valve. And that would be a TESV, but if this is closed, this pipe is not protected. Now, why will this LNG keep gaining heat? Because it is at minus 200 and some odd degrees Fahrenheit, and the environment is always leaking heat. You can never stop heat leak. Heat will always transfer from a hot location to a cold location. No matter how much insulation you put around it, there's always be some amount of heat leak. So you get this heat leak, pressure builds up, you get past the critical point. At critical point, there's no difference in density between the liquid and the vapor, and the pressure rises up very rapidly, and then boom, you have an explosion. And that's what happened at the Freeport LNG plant in 2022. There was this type of an explosion. Now, typically, that just the levee itself, before any secondary explosion, has enough power to rip out piping and other equipment at the plant. And what would happen is, if this is a flammable liquid, which LNG is, it would take out electrical connections, etc., which becomes a source of ignition, and then you end up with a levee. Boiling liquid expanding vapor explosion is what it's called. A steam vessel can levee, but a steam vessel does not have a secondary explosion. That doesn't mean it can't be a violent explosion. It can be a violent explosion, but it's even more violent when you have a hydrocarbon in that vessel. This is a picture of a vessel that levied. This was a reboiler, and you can see here the reboiler tubes. Well, this was the outer shell of that reboiler, and it's shown in the next safety moment even more vividly. But this is a vessel that was once circular that levied, it ripped apart. Characteristics of a Blevy, rapid pressure release. It can produce a shock wave. And the secondary fireball, if it happens to be a uh, a flammable liquid that's in the container, can also have a shock wave. May or may not have a shock wave, the secondary, depending upon the conditions of the material that's exploding. Flying debris, that's another thing that I did not mention, but flying debris certainly rips out many parts of other pieces of equipment or other fuel carrying, piping, etc. So flying debris is a major concern. In fact, when I talked about rupture early, I didn't talk about one of the things that's not taken into account in the calculations of the heat transfer or the hazard is the amount of earth and debris that gets blown out of an opening. The initial blast of a pipeline rupture has 4 times the amount of gas flow than the final steady state blowing, because what happens is the final steady state, all the pressure is down and it's just being fed by the pipeline, continuous flow of gas. But that initial pressure energy is not counted as part of the hazard associated with it. In fact, one of the ruptures that occurred in Edison, New Jersey, blew a crater in the ground. Think about the numbers: 140 feet long by 65 feet wide by 14 feet deep. Think of the amount of earth, rock, asphalt, and everything else that was blown out of that opening. And that's very significant. So with a levee, you also get a lot of shrapnel associated with it. Many times, shrapnel will be found a quarter of a mile or to a half a mile away from the levee because it has that much energy. Conclusion: yes, pipes and LNG vessels can levee. They typically don't because of administrative controls, such as making sure that relief valves are always on piping and that the vessels are always protected. Safety moment number 4 is a culture of safety, safety culture. And many times you'll go into certain plants and you'll find they're not inhabiting a culture of safety here. One of the things that the CSB, Chemical Safety Board, did was they made a video. It's 55 minutes and it is worth your time to review it. It's called The Anatomy of a Disaster. I called it Anatomy of an Accident. Prior to making this video, many of the same things that they identified, I had identified in my training, which I called Anatomy of an Accident. In this case, they called it Anatomy of a Disaster. Very worthwhile seeing it. It's 55 minutes. In that video, Professor Trevor Keltz stated, if you think safety is expensive, try an accidents. Accidents cost a lot of money, not only in damage to plants and claims for injuries, but also in the loss of your company's reputation. I know of one plant that was completely built. It was an import terminal, LNG import terminal. Their commissioning cargo was en route to that location. 3 miles away from it a year earlier, an LNG plant had a collapse of the roof, a fire inside the LNG plant while men worked inside. 40 people were killed. That plant was totally shut down. Not only was that plant totally shut down, dismantled, but the plant that was being built on the very week of commissioning, because the commissioning cargo was en route, their operating permit got filled, and those tanks, I live about a mile from those tanks. Those tanks never saw a drop of LNG. There were 2 full containment tanks. Now, a lack of safety culture. On October 2016, a reboiler exploded in Baton Rouge, Louisiana. The accident investigation report concluded that process safety management program deficiencies at the facility during the 12 years leading to the incident allowed for this heat exchanger called a reboiler to be unprotected and overpressurized, ultimately rupturing. The CSB investigation revealed a poor process safety culture. That was the key thing they found here. Lack of management of change, lack of pre-startup safety reviews, process hazard analysis, lack of process hazard analysis, lack of procedure programs. They were very casual about how they operated the plant, and the end result, they ended up in this case with a number of people being killed, and I'm looking for the number on here. I don't know. This one's not the one where the people were killed. There's another one that I'll mention where it shows 16 people killed. I don't think anyone was killed on this accident, but you saw this is the results of that accident. You see the reboiler. This was the plate of steel that you were looking at earlier that was brought inside, and this is the reboiler itself that was brought inside. And what happened is they allowed heat to enter this reboiler. It contained propane, and the relief valve had been blocked, and the end result was this levee. But the issue here was really the culture, and that's the key thing I bring up. And I conclude this very strangely. I said back in 1600s, Elizabeth Barrett Browning wrote a poem, "How do I love thee? Let me count the ways." I said, what a strange way to end a safety moment. Well, each of us, myself, yourself, your fellow employees, your coworkers, the citizens that live outside your plant, they all have someone that loves them or that they love. Everyone deserves to come home safe at the end of their shift. That's putting it in a nutshell. And I've seen many a times where I've visited people who are injured on the jobs and they're permanently disabled. And I see not only the worker injured, but the entire family has been injured. Next, we're going to talk about the difference between deflagration and detonation. You've probably heard the word deflagration many times. Deflagration is a slow-moving flame front. So often we see in testing that they'll pour LNG into a pool, and someone from far away will go with a torch and light the vapor cloud, and that flame will move slowly to the pool of LNG and just continuously burn. That's called deflagration. It's a slow moving flame front. Detonation, on the other hand, you've probably seen many times where you're watching a war movie and you're looking down from the plane bombardier site and you see bombs hitting the ground, and you see as the bomb hits, there's an explosion, but then there's a pressure wave that ripples out far away from the explosion and just goes ripples out all the way around the explosion. That's a pressure wave, and that pressure wave is what's associated with a detonation. And a pressure wave can kill people, much more so than a deflagration, because a deflagration, you only have to worry about the heat. But the detonation has this pressure wave that goes way beyond the heat zone of the fire. So if you look at it, 1 psi overpressure is what it's called. And think about your body, 62, let's say you're 72 inches high and let's say 20 inches wide. That's 1,440 square inches being hit by a 1 pound force. That's 1,440 pounds pushing against your body instantaneously. Well, that can cause lung damage, possibly fatal injuries, internal organ destruction, break windows, etc. 2 pound, you're a significant probability in significant uh, danger of death. 5 psi, instantly fatal. Complete destruction of buildings. Contrary to many beliefs, although unusual, vapor from LNG can detonate if it's very turbulent. I did my PhD dissertation on turbulent flows of natural gas inside engines, inside natural gas engines, the cylinders. If you provide enough turbulence in swirl and enough turbulence in tumble, then you can actually control the temperature and the emissions associated with that flame by increasing its turbulence. If the flame front is extremely turbulent, you can also end up with detonation. You can also end up with a transition from deflagration to detonation. How does that occur? Let's say you're in a crowded pipe rack and you have a gas leak and it starts to deflagrate. And as that flame moves faster and faster through the pipe rack, it's going around piping, and all of a sudden it gets turbulent enough where the flame front becomes supersonic. Once you got a supersonic flame front, you have a supersonic shock wave ahead of it. And that's where you end up with deflagration leading to detonation. Preventing air fuel mixtures from occurring where they are not intended. That's our job. And that's our job. Where are they intended? Inside boilers, inside uh, process equipment where we expect to have flames, but not in the environment of the plant proper. Preventing a levee or boiling hydrocarbon is critically important in any petrochemical plant. Safety moment number 6, do not peel back the layers of protection. And what I mean here is, I'm keeping an eye on that time, what I mean here is that everything has layers of protection when designed. Take, for instance, your LNG tank. Well, what if we get a leak in the LNG tank? Well, one layer of protection is you have sensors on your tank that will warn the operator and he can take certain actions. But you're using 9% nickel steel. That's a layer of protection so that your tank can withstand that that cold temperature and not crack and not become brittle. Another layer of protection is you have a dike around it. Oh, that provides, if you do have a leak, that the leak doesn't run down the street into the sewers like it did in 1944 in the Chicago LNG spill. Another layer of protection is you might have insulated concrete on the dike area so that if there is a spill, it produces much less boil off. You might have foam generators that put a layer of foam over the LNG. So these are all layers of protection, and you have to watch out not to remove layers of protection. I remember one incident, and it's part of this presentation somewhere in here, where layers of protection were removed, and then eventually there was an explosion and two people were injured. Uh, then, in fact, this is the one. A 4,000 psi CNG compressor exploded, injuring two employees. Layers of protection were breached over a period of time. And here's what happened. This let me just make sure the next slide is what it is. Okay, this this compressor was operating and it kept shutting down on low suction pressure. So what happened? The mechanic went there, says keeps tripping out on low suction pressure. He removed the suction sensor. Well, that certainly eliminated the problem. No more suction sensor, no more shutdowns on low suction pressure. Why was it shutting down on low suction pressure? Because the new compressor that was being built next to it was tied into the same intake valve. So what happens is when the new compressor, when they would leave at night, the guy would hit the ESD button and go home, and the other compressor, and what that would do is shut the inlet valve to both compressors. So when the compressor came on, calling for gas, and came online with the suction valve closed, it was pumping up against us with a suction at the inlet. Well, what happened is there were also devices on the compressor that would look for temperature. Well, that caused the compressor to overheat because you're putting in work energy and no gas is flowing through. So the temperature should have shut it down. But over time, the temperature sensors, which were attached to the pipe, had gotten loose and they were not touching the pipe. And over time, the insulation that was around those temperature sensors fell off the pipe and fell to the ground. It was not maintained properly. So that also was another layer of protection that was. So what were the layers of protection that were failed? Engineering failed to design it correctly to have one plant shut down the the inlet valve to the other plant. And so there was an engineering layer of protection that was missed. The maintenance person taking the suction valve out, the suction sensor out, that was another layer of protection. The mechanics foreman who looked at that and said, okay, and just filed away the paper. And then the period of time that took place, it was months after that suction sensor was removed, then it had probably operated on that vacuum condition many a time, but no one ever followed up on that repair. And so these are all layers of protection, some administrative and some just outright technical in nature. And those layers of protection are all removed. It's like a layer of protection is like Swiss cheese. You lay it down, you have, oh, there's a hole in the Swiss cheese. That's where an accident can happen. Put another layer down, the holes don't line up, the accident's prevented. Another layer, the accident's prevented. For instance, if those thermocouples or temperature sensors were not did not experience a lack of maintenance, they probably would have stopped the accident from happening. But both the suction sensor missing and the temperature not reading properly, you had the accident. So what happened eventually? The compressor's operating. The seal on the inlet of the first stage compressor, seeing a vacuum, got hotter and hotter. It failed, sucked air into the compressor. Then you have air, some residual natural gas, and lubricating oil mixing together in the fourth stage. Ba-boom! And when I got there, my men were starting to they were on the men that were under my responsibility were starting to depressurize the plant, and I said to them, "Stop." That I want to take samples of the gas. They said, "What are you looking for?" I said, "I'm looking for air." And the reason why I was looking for air, because both manifolds, a heat exchanger is nothing more than manifold and manifold with a bunch of pipes going through it, a fan underneath blowing air across those pipes. The pipes have fins on them. Both manifolds, which were 1.25 inches thick, were blown in half. So right away, I looked at that and I said, the only way that could have happened would be ignition inside those manifolds. So what I was looking for was air. Sure enough, went to the lab and they found 2% air in the gas. And what that meant is that there was a lot of gas stored in there, but then eventually it started compressing air instead of gas, and that's where it got that air gas mixture in the last stage. The analysis showed that a failed component inside the machine caused a spark, caused a hot spot because it was metal on metal wearing, and uh, and that's what caused the explosion. It was a removal of layers of protection. LNG on wheels. This is an interesting one because LNG has always been, oh, this big fear about LNG on wheels. Well, tens of thousands of trucks carry LNG every year across the United States. And you know what? They also carry gasoline and propane. Is there a hazard of transporting LNG? Yes, there is, but it's a manageable hazard and it's an acceptable risk. And it's done all the time, same as gasoline trucks, same as propane trucks. And that hazard is considered acceptable, but doesn't mean we can get lax. The operators have to be trained, they have to be qualified, the equipment has to be inspected for being mechanically sound. In fact, when an LNG truck comes into your plant, it's your responsibility, the truck drivers too, but your responsibility. Take a walk around that truck and make sure it looks like it's a safe truck, which means that the tires have threads. Does it look like the air brakes are properly has to have the proper amount of movement? Is the operator using chocks? Is the key taken out of the ignition while the guy is unloading or loading? And quite often, what they do is they have the key on a big elephant ring that you put the key onto the hose so that there's no way that that key can be used. But of course, people are sometimes lazy, and who stops someone from getting a second key and leave just using the key and not putting the elephant hose on the key? So if you, as the operator, whoops, I just lost my lavalier mic, so we'll click back on. So as you as the operator see that they're not taking the proper precautions when loading or offloading, you have to take action to stop that work that's in progress and make sure that the deficiencies are resolved. Do they have accidents? Yes. Here's an LNG tanker that got hit in the rear. As you can see, there was spillage of LNG. There was no ignition, but there was spillage of LNG. You can see that by all the frost that's around the tanker and the end of You can imagine this is where all the piping is for removing the LNG and adding LNG. It's all back here, the valves and relief valves, etc. Conclusion: transport of LNG, gasoline, and propane all have their unique hazards. Our job as engineers and operators is to ensure that only safe practices are employed when transporting LNG. How else can LNG be transported? By ship. And a lot of the work I've done has been site-specific work on import and export terminals. So a lot of work can be done on ships. And you say, how much does a ship hold? Well, let's say an average ship is about 3.3 BCF, and an average large tank is about 3.3 BCF. And how much energy is that? Well, you can run your house heater for well over 1,000 years, 24 hours a day, 1,000 years, and not go through a BCF. So think about that amount of energy. Now times that by 3.3, and you get an idea of how much energy a an LNG carrier is carrying. How much energy is in an LNG tank? Very significant amount. In this case, I'm going to look at good communication is essential for reliability, and safety and reliability. A lightning strike, this is one of the jobs I got called out to. I was out to dinner with my family and I got called, Steve, there's been a bad gas leak on such and such location. I left my family and went, it was a Saturday night, and I went to the job site, took over. I became the PIC, pick on the job. And a lightning strike had hit a hydrant about a mile away from this location. At this location, the energy from the lightning jumped across to a water main and blew a hole in the gas main, which was operating at 60 psi, about the size of between a dime and a nickel size. A good blow of gas, but the street was paved When I got there were bubbles coming out from the street all over the curb line. When I said, this is a concern because under the pavement is pressurized with 60 psi of gas. Now it's probably less than that because it dissipates, but I know it's pressurized, and my initial concern is gas getting into those houses. So I said to the customer service person, he's the person that would go into the houses. I said, go in the houses, make sure there's no gas at the front wall. Front walls where you'd expect gas to be coming in. The customer service person came back to me and said, I've secured these 4 houses. I said, good. Now check the manholes and radiate out until you get no gas readings in the manholes. And as he was going away, stepping away from me, I said to him, wait a minute. What do you mean that the houses are secure? And he said to me, well, I mean that the the curb valves have been shut. I said, that's not what I asked you. I asked you to check that the front walls are clear. Oh, well, in his language, secure means curb valve shut. For me, secure means those buildings aren't going to explode. And we have had cases where we're outside working, jackhammering, and boom, a building explodes because gas is getting into the building. So I said, now get into the buildings. He says, I can't. Nobody's home. So I said, well, we have the fire department here. I said to the fire lieutenant, we need to get into these buildings. Boom, 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 boom. They open up the buildings. Guy goes in. Okay, the front walls are clear. Now do the manholes, etc. On this job, the guys were able to excavate an opening over where the gas was blowing, which now the gas is vented at least, going to the atmosphere. It's not pressurizing the underground. That was the important thing. And then I had them excavate an opening about 200 feet away where we were going to install a shortstop and close the valve, the shortstop between the shortstop and the valve. We could isolate that section and repair it. Now, after we were able to slip a atom sleeve partially over the leak, but it was still about 10% leaking. But after the firemen and the news media and everybody else left, the guy said, let's go in the opening and push that atom sleeve on the rest of the way. I said, no, you wait. I said, tomorrow's Father's Day, and I want everybody to be home tomorrow. The daddy's home tomorrow, not in the hospital. We're going to wait till the opening is dug and we get the shortstop in and we get the valve closed, and then we can work on this main with no gas blowing. And that's exactly what we did. Here's another communication error. It's a Sunday morning. I was chief engineer at the time, and I get this call from the dispatch saying, Steve, we're going to lose part of the district. I said, what's the matter? He said, it's your LNG plant. I was in charge at that time of 14 LNG plants, 14 propane air plants. So I called the LNG plant. I said, what's going on? Operator says to me, look, Steve, every time the dispatcher asks for more pressure, I give him more pressure, and he's complaining that he's getting less pressure. If I give him any more pressures, I'm going to blow the relief valves. I said, where are you reading this pressure? He says, on the outlet of my pumps. I said, which valve are you closing? He said, the inlet to the vaporizer. So the pressure is building up between the pump and the vaporizer. And what he's doing is pushing the pumps into recycle. I said, that's not where he needs the pressure. He needs it outside the plant. He says, well, I'm having another problem. I said, what's that? He says, I have 4 vaporizers on their minimum flow, and they were all fluctuating up and down. I said, well, how do you have them set? He said, on automatic. I said, put your vaporizers on manual. Start opening up the valve between the pump and the vaporizer. Start flowing through the vaporizers. Bring up each vaporizer on manual and leave the last one on automatic. All of a sudden, the pressures on the outlet of the plant rose. The uh, the district was saved. The pressure on the outlet of the pump started to drop the way it should, and the day was saved. I was 300 miles away from that plant. It was a Sunday afternoon. Where do you think I was at 9 o'clock the next morning? At that plant. I flew out, rented a car, went to the plant, and as soon as I walked in, the plant superintendent says to me, Steve, isn't it true when you have higher pressure on the outlet of a pump, you got more flow? I said, no, it's just the opposite. Everybody in the lecture room, let's go over basics of pump operation and how we went over pump curves, net positive suction head, pump efficiency, flow versus volume, etc., and how the pressure drops over a period of as your flow increase, the pressure in the outlet of the pump drops. The problem was communication. When the dispatcher said I need more pressure, The LNG plant operator never understood. He means outside the plant, not at the pump. Chief engineer quickly understood what the problem was. No credit to me. I mean, it was common sense. What we were missing was a lack of cross training so that the communication has to mean the same thing. And be careful when you're dealing with people from other cultures, other continents. They quite often have a different understanding of word meaning than you might have, and a different culture. Like in some cultures, it's considered rude and improper to say no. So they might say, well, that's not as I think it would be, which means no, in that culture. So you have to be careful about understanding what's being said, and you need to identify if you think there's any doubt, you have to dig further. You need to have, this one deals with technical knowledge. Everyone in the plant must be technically knowledge of what is going on. You need QA and QC. QA is training, QC is testing. It is a good practice to go around to your plant and ask questions. I went to one plant and I was doing an audit on the plant, and I went up to the top of the tanks and I saw 3 N-rafts that were broken. All 3 of them, the person had closed the valve before retrieving the tape upward and pinched the tape. And I said to him, how are you operating without your N-rafts? He said, oh, we use the pressure at the bottom of the tank to determine the level. I said, okay. I said, do you take into account the density of the LNG? Person looked at me, the density, what's that? So they obviously were not taking into account the density. You could have a density anywhere from 26 point something up to 29 pounds per cubic foot of LNG, which is certainly going to change the pressure that you're reading. So you can end up overfilling the tank because you're thinking of using the wrong density in your equation. So that was something I had to train them on. There were many things in that audit that were bad, but that was one that really sticks to mind because it had been about 3 years with those N-rafts broken. I'm sure after my audit, they got them repaired. Some of the questions might be as shown in the following. I'll go around, I'll ask. So let me ask you a question. A recondenser uses subcooled LNG to cool and then condense the superheated boil-off gas, lessening the need for pipeline compressor use. Is that true or false? It's the kind of question I would ask an LNG operator at a plant that has vaporization or that has a recondenser. A recondenser can only be used when vaporizing. LNG pump cans must be supplied with what type of LNG and NPSH? Subcooled LNG, positive NPSH. What are some reasons for rising tank pressure? And there are many, many reasons that the operator can give you. You start the top load of a tank, to top fill a tank, and the pressure all of a sudden drops, and you have to stop loading the tank. What's going on? I'm putting stuff into the tank. Why is the pressure dropping? Well, if the vapor space is warm and the LNG is cold, it's going to make the vapor cold and contract, and the pressure is going to go down. So you have to pre-cool the tank before you do a top fill. A hurricane is coming tomorrow. What do you, as a prudent operator, need to do today because the hurricane's coming in tomorrow? Bring the pressure of the tank down. New production contains 1% nitrogen in your LNG. What concerns might that LNG operator have to consider before this situation where you're going to take on this new LNG inventory? And certainly, what we spoke about earlier is nitrogen stratification, but also boil off. We'll talk about that momentarily. And your boil off may flash to where you're getting a very high percentage of boil off. And there we go. Okay, lessons learned. Highly revered consultant said to me at one time, it's far better, in my opinion, to learn from somebody else's mistakes than from your own. And you can certainly see why. And we have to move along because the clock is ticking faster than I'm going. Send out. Let's talk about send out. What is send out? Send out is the gas that you're going to take LNG, heat it up, turn it into a vapor, and send it out. That's called send out. Pipeline gas is typically 1035 BTU. Send out gas is typically 1050 to 1100 BTU. So, and what about tail gas? That's all your regeneration gas that comes off your regeneration of your mold sieves, etc. Gas that comes off and has your outlet of your heavy hydrocarbons dumped into it. It can be all over the map. Tail gas, I went into one plant and I walked over to the gas chromatograph and I looked at the tail gas. I said, do you realize that you're sending out 12% nitrogen out to your district? He says, "Oh yeah, that's typically happens when we're vaporizing." I said, "Well, that's in violation of the FERC requirements, and also we have therm billing here, so that's in violation of the therm billing. So we had to make some changes there. But that's something that operators says, oh, we always do it that way, and I got to be careful of we always do it that way thinking." Because that's how we always do it that way, and 99 times there's no explosion, and on the 100th time you get an explosion. FERC guidelines are you must be under 1110 BTU per standard cubic foot. You must be under 1400 and Wabi index, and that's a unitless number. You must be within 4% of your normal Wabi index number, and you must have less than 4% of inerts in your gas. And it also has another requirement based on heavy hydrocarbons. C+4 hydrocarbons, I think, is 1.5% maximum, but you wouldn't typically have that anyway. But you can end up with a tail gas is mostly methane, nitrogen. If you're liquefying, you have 1% in your feed gas coming out, and you condense out all of the methane, ethane, propane out of your gas. What's left but nitrogen going in with your tail gas? It's going in with your tank, coming out as bog. So your bog coming out of the tank is mostly methane and nitrogen. And you can get a significantly high amount of nitrogen, as we did with that case where we had 12% nitrogen. Conclusion. In this safety moment, it's not intended to say what is right or wrong, good or bad. I do not know enough about your specific plant. If you said, well, what about my plant? And can we add on RNG, which is renewable natural gas? You get a landfill gas, etc. Really depends on very plant specific, very RNG plant specific. And the gas that you're getting out today is not the same gas you're getting out tomorrow and 10 years from now, because the garbage changes. Where you're taking the gas out of the renewable natural gas plant changes, etc. You need to do an MOC anytime. It's a management change. Anytime you change anything associated with your plant operation, in particular, what your feed gas is going to be. Certain safety moment number 12, ring out your instruments correctly. Now, what does ring out mean? It means that if you have an instrument cluster and let's say this is supposed to open a valve when it gets hot, that you put heat here and see, does it open the valve? Or put cold here and see, does it close the valve? If you don't ring it out, you're not going to know for sure what is going to happen. I was at a portable pipeline job, and I was going to be the consultant leading this project. And the day before the job, I went out to the equipment to look it over, and I see an instrument person putting in new instrumentation. I said, what are you doing? He said, I'm putting in redundant instrumentation. I said to him, make sure you ring it out before you complete the job. He says, okay. The next day, we were on the job. We start the LNG flowing through the vaporizer. The valve was supposed to open to allow more heat from the boiler to go into the vaporizer. Instead, it saw the cold LNG and it closed all the way down. What happened? Raw LNG went into the underground piping. The underground piping cracked because it's non-cryogenic piping. It was operating at 80 psi. Of course, you had the whole street. We actually felt the street lift up until it blew out, and then that was the vaporizer truck and everything. You actually feel a little bit of a jolt, and then with the gas blowing, we had to now deal with a cracked gas main. Where did it crack? At the first well. I told them dig up and where you find the first well, you'll find a half moon crack. Now you might say the well is the strongest part. Not on the cryogenic conditions. It's not. It's the first point of discontinuity in the piping, and that's where the crack ended up, exactly where I expected it to be. But it shouldn't have happened. We should have rang it out properly. Cover gas, vacuum gas. If you own an LNG tank, you have cover gas, which is also called pad gas. Maybe called pad gas, maybe called cover gas in your plant. And you also have vacuum breakers. Cover gas is a connection to the pipeline that basically says if your tank gets down to real low pressure, let's say 0.1 psi, it's going to start supplementing gas into your tank from the pipeline. Well, why? Because it's dirty gas, because it's better than having the tanks collapse under a vacuum. So you want to prevent that gas from that tank from collapsing. But in some plants, operators have closed the valve that goes uh, from that pipeline to the tank, because in fear of, if that regulator ever fails, I'm going to get this gas, this wet gas into my tank. I won't know it. How do you know if I go to the operator and ask him, is your valve on your back cover gas open or closed? He may not even know what I'm talking about. So you need to make sure people are aware of systems, safety systems that are never called upon, but that should be there in case of an emergency. Cover gas is one of them. Also, you have vacuum breakers on your tank. These are relief valves that relieve inward. They take air from outside the tank and allow it to blow inside the tank. And you say, that's terrible, because now you have air inside your LNG tank. Yeah, but it's better than the tank crushing. And as you'll see in a moment, air inside of an LNG tank, unless the right mixture, cannot ignite, and there's no source of ignition. You could say, well, what about static electricity? Yes, that could be a source of ignition. Negative pressure protection on tanks. This is just saying the same thing I just spoke about. Safety moment number 14 is a very interesting one. You used to look at your boiler, if any of you have a home boiler, and you look at it and you see the sight glass, and it shows you the level of liquid in your tank. And you believe that sight glass. But what if the density of this liquid is not the same as the density of this liquid? Well, under what cases would that be? Well, let's say this liquid is at 220 degrees Fahrenheit, let's say boiling at 5 psi, and this liquid is at room temperature. Well, it's not going to be the same density. So this is going to read differently than this. And a minor change. What if this has got a lot of bubbles in it because it's boiling? Well, then this is the bulk density here is going to be very light, because half of it's filled with bubbles, or some portion of it's filled with bubbles. That's going to be certainly a lot different than this. So there are a number of issues that can be shown. What if there's foam on top of your layer? Now, when would you get foam? Well, let's say I'm running an amine system. Amine uses amine and water solution. Well, amine foams pretty easily. You get foam on top of it. Now, is this reading correct? No, you're trying to read this level and you're reading it incorrect. Fortunately, most of the amine absorbers will have a sight glass on it where you can look and see if there's foam and siphon off that, or skim off that foam off the top layer of the liquid. Let's add some instrumentation to this. So now let's add some instrumentation, and we might think, oh, now that we're adding electronics, we're doing better. Not so, because this electronics has to be calibrated for the correct liquid and for the correct density of that liquid. And also, it's not going to get rid of this foam issue at all. So now you're adding another layer of complication, because there's electronics involved that has to be calibrated correctly. Let's do a different type of, and this is a type that's done most often, where you put a sensor here, a pressure sensor here, a pressure sensor here, and you send that differential pressure by way of a 4 to 20 milliamp signal to your control center. Again, you run the risk of these pressure transducers have to be calibrated correctly, and they have to be the correct pressure transducers for this application. You would not want to use a 1 to 3,000 psi pressure transducer on a liquid that's going to see only 6 feet of water level as a height. You use the right transducer, etc. Let's talk about something that's very much a concern, and that is, let's say that this distance is 6 feet from here to here. And let's say that your zero offset, there's two calibration that you do, zero offset and span. Let's say your zero offset is off by 1 foot. So when this level gets up to 5 foot, you're reading, when your level gets up to 6 foot, you're reading 5 foot. So you think you still have room. So you keep adding liquid, you still have 5 foot, keep adding liquid, still have 5 foot, keep adding liquid, still have 5 foot, now you got 26 feet of liquid in here, but you're only reading 5 feet. So you keep adding liquid, and eventually that's what happened at the Texas City refinery, where they had a major gasoline explosion with 15 people killed and a devastating explosion that destroyed a lot of the plant. Continue on. Safety moment number 15. Horseplay has no place in your plant. I had a pressure test being done on a 300,000 pound hour boiler that operated at 800 psi, and that boiler was being pressure tested to about 1500 psi. The sub foreman, who was a very good employee, the sub foreman took a gauge, screwed it on, and started pumping water into the boiler. And he filled up the boiler with water and then started pumping water into the boiler, watching the gauge. It's not moving, watching the gauge. It's not moving. And then eventually it started moving. When he got up to about 1,000 psi, the tube sheet and the not tube sheet, there's a mud drum and a water steam drum. The tubes where they entered the mud drum and where they entered the steam drum started leaking. What happened? Somebody spun the gauge on him. It was a prank. And so when when the boiler was actually seeing 2,000 psi, it was still showing zero. When it's showing 3,000 psi, when it was at 3,000 psi, it was just coming off the zero peg. So it was a prank that ended up destroying the boiler, shut the plant down for a whole year. I remember getting on a plane, flying out to Erie City and saying, I need a new boiler right away. And they said, get in line, you and everybody else. And that plant was shut down for a full year. Uh, I protected the sub foreman because he was a good person, just not skilled, who did not have the proper training, and by suspending him because upper management wanted him fired. The person that pranked the guy by spinning the gauge, he was fired. The sub foreman, I suspended him for a week, which I caught hell for doing that, not for firing him, but it was shouldn't say hell, heck. Uh, but it was, I think, the proper thing to do. Hydro tests should always be done using calibrated gauges and at least two gauges on the. I prefer having a dead weight tester on the site, but at least two gauges at different points on the uh, on the vessel that you're testing. Why 2 points? Because let's say there's a valve closed where you're testing it, you're getting a wrong reading. We don't want two gauges both getting a wrong reading. Safety moment number 16, rigging and outrigging support cautions. There are two incidents I'm thinking about. One was when a cable went through a precast vault. The rigger came and put a cable through the precast vault. And the way the precast vault was made was it had two openings on the side. And the openings were done by putting a 12-inch pipe across. After the casting was made, they took a welding torch and just cut around the pipe, and now you had this window which had really sharp edges around it on each side of the casting, and it was a manhole casting. So what the rigger did when the truck came is he put a cable through, and right along the sharp edge, he then hooked it to the crane, lifted it up. The truck went and pulled out. Before he got to let it down, boom, the cable snapped and cracked into a million pieces. I don't know if it was a million, certainly enough pieces to make it unusable. And it took another 6 weeks before we can get another, which pushed the job off by 6 weeks. Did not engage the brain before taking the foot off the clutch and did not also check the rating on that cable. That was another issue. Second issue that happened was we were removing a insert from a shell and tube heat exchanger. So the shell is the outside, the tube is the inner part that's removed from the shell and tube heat exchanger. It weighed about 10,000 pounds. It was about 60 feet off the ground. Crane was hooked up to it, removed the tube bundle. As soon as the full weight of that tube bundle got on the crane tipped over, crashed into the plant, and got hung up on the structural steel. When I got out there, I looked and I saw the outrigger sunk deep into the ground and hydraulic fluid on the ground. Now, the operator said to me, "Well, the hydraulic tube hose broke." I didn't question that, but I did see that. I said, You didn't have enough dunnage or any dunnage underneath your outrigger. That's where the problem is. And when you have an outrigger, you have to make sure you have the proper amount of dunnage. Dunnage is 6x6s or 8x8s pieces of, typically it's 8x8s or 12x12s, pieces of lumber that go in one direction, then cross in the other direction. So that gives you a big footprint for your outrigger to land on. Without having that, when the weight got on the outrigger, it just went squished right into the soil and the crane tumbled over. So this was operator error, and it was a rigging operator's error. Now, it's been many years after that, but now I start to wonder, did the hydraulics really fail, or did the operator, who was not very trustworthy, is also the same operator that dropped the crane? Maybe somebody cut the hose. As many years after the fact, who the heck knows? But one thing that was clear, you need to put dunnage underneath your outriggers. Hackers, cybersecurity. Hackers have gotten into the U.S. government. And actually, I got this story and I asked AI to summarize it for me. And what happened is hackers got into the U.S. government, Department of Defense, Department of Treasury, Homeland Security, and other agencies, not by hacking into them, but they hacked into their software updates. So let's say you have Microsoft 365 and you get an update, says it's now been updated. You take that update, you trust Microsoft, but if Microsoft gets hacked, you get hacked. So you have to be aware not only of the fact that your systems can get hacked, but also that your software, that your agencies that you provide or being provided with the software, they can be hacked. That's what happened in this case. Experts determined that it could take years to understand the full ramifications of this breach. This breach had occurred for many, many months before it was uncovered. And the reason why it wasn't uncovered is they made it look like all the normal operation of the system. Let's say you go into Excel, you expect an Excel spreadsheet to come up, you put data in, you expect that data to be stored, etc. It was silently hiding in the background, sending information on all the information from the Homeland Security, Department of Treasury, and other federal agencies to an outside country. And this attack was attributed to Russia, but you never know what the real infiltrator, who the real infiltrator was. This was deemed to be a very sophisticated infiltration of the trusted vendor's software. Lessons learned: the need to be proactively defending your cyber systems. I do know of several companies that have had valves open and closed where they did not give the commands, but they were being controlled from outside the company. I also know of an event, and you probably recall it, where gasoline was short in the southern states, and in Florida there were gas lines because of a ransomware attack. And my understanding of it was they paid the ransom and they got their system back up and running. But their infrastructure for moving gasoline from location to location was totally compromised by way of ransomware. Safety moment number 18. Expect components to fail. Okay, I'm always expecting components to fail. If I go to a plant and I see that there's a spring hanger, that's the highest point in the plant, and where would that be? Probably at the top of the tank, where your piping comes over the top of the tank and there's a spring hanger there. I can pretty much be sure that they're not going to set up rigging or scaffolding and check the spring hanger to see if it's still moving or if it's frozen in place. And I shouldn't say I'd be sure of that, but it's an area that I would be concerned about. And I'd ask about, let me see the records on that and who did that. And I'm going to talk to the operator or the mechanic and tell him, how did you go about doing that? If he says, well, I walked out on there and checked it, that's not going to be true because it's unsafe to walk out on there without a harness, et cetera, about 200 feet off the ground. Or I'll see a gas detector that's way up in a location that's really hard to get to. I'd ask, when was the last time that gas detector was checked? It would be very common for me to walk into a control center and say, okay, let's make a mock drill. This pipe has just ruptured. Take all your emergency actions. And they would literally roll trucks out to the location, put valve keys on, turn the valve 10%. I wouldn't want to shut the system down, but just make sure that the valve key, things we find out. We weren't able to find the valve. The valve was improperly numbered, wrong tag number on the valve, that normally hammered into the valve ring. The valve, when we went to spin it, spun freely, meaning the gear's broken, or the valve was unable to move it at all. So there's a number of things that you find by doing these kind of tests, and also that the operators, the dispatchers, knew what to do. They get the red books, which are the emergency books, turn to the right location, send the right trucks to the right location, right valves, and go through the whole sequence. Everything short of actually shutting the system down, but rolling the trucks. A lot of things we find is the truck gets to the location. They don't have a valve key on the truck. Duh. And I did the same thing in the plant. I said, okay, you now have a cold spot on T1. It's a cold spot on tank 1. What actions you're going to take? And the operators will go through their steps, things that they would never think of doing. They'd rather be talking about the game than thinking about what if situations. But those what if situations are what we have to be prepared for. I'll give you a for instance of a job, and this is one that this one covers. There were 2 molten carbonate pumps. Benfield system removes CO2 from gas stream. So molten carbonate is melted salt, kept hot. These pumps are a very corrosive environment. And the way the pumps are operating, they got a check valve on the outlet of the pump. The pump is driven by a steam turbine. And there's 2 steam turbines with 2 molten carbonate pumps. Typically, every shift you swing from one turbine to the other turbine. The mode of swinging was you shut down this turbine, the flow back pressure of the flow slams the check valve closed, and the next pump is put online. So that now you have the next pump taking over the service. But what happened this time is the check valve stuck in the open position. Expect these things to fail. Now, when they went through the HAZOP, which is the hazard and operability study, they say, what if the check valve fails? They put in a reverse clutch. Reverse clutch is a device that if it sees the pump or the turbine spinning backwards, and how would the turbine spin backwards? Let's say the turbine had no steam, and the pump had the flow going backwards through the pump that would make the pump spin the turbine backwards. Well, this reverse clutch would lock and close and prevent that rotation. Well, it just so happened the reverse clutch was put in when the plant was built and never maintained. So when it was called on to operate, it did not operate. The turbine went into overspeed. There were 6 men working there trying to swing the pumps when it happened. They heard it run into overspeed. They ran. The turbine blew up. The blades were everywhere throughout the insulation. The 4-inch diameter shaft blew out of the casing, bent like a pretzel, and that turbine was out of service for a full year. Fortunately, all the operators were scared, of course, but no one was injured. Thank God for that. But it could have been a very serious situation. What happened? Something that's not called upon to operate was never maintained, and bada boom, there was the result. What about your vacuum breaker that we spoke about earlier? When was that ever maintained? Can you tell me if that's ever been used? Can you tell me if it will operate and if it's called upon? The vacuum breaker, or the pad gas, I should say, or cover gas system. I'll leave you with that question. Lessons learned, expects components to fail. Safety moment number 19, understanding combustion. And I'm looking at my time carefully. We still have some time, a good amount of time left to finish this properly. Asphyxiation due to a lack of oxygen. Understanding combustion. There are 3 significant hazards associated with LNG. One is asphyxiated due to lack of oxygen. It displaces air. If it displaces air, whatever you're breathing could be LNG vapor, could be air. If you go into a nitrogen environment, you drop like that. Why? How does your lungs work? Your lungs are a very high area, surface area of a semi-permeable membrane. And what it does, it looks at the 2 sides of the membrane. I say it looks at, it doesn't really look. But what it does is it essentially concentration driven. So if it sees a high concentration of oxygen molecules here and a low concentration here, the oxygen molecules go across the membrane in that direction. If it sees a high concentration of oxygen molecules here and none here, the oxygen molecules go in that direction. So if you take a breath of pure nitrogen, what happens is it literally takes oxygen out of your bloodstream. It's not that you're not getting any oxygen in your bloodstream. It's literally whatever oxygen is in your bloodstream is in your hemoglobin. It's taking it out because you have on this side no oxygen at all. So you have to be very careful. And people might think, oh, I can hold my breath for 3 minutes. Really? One breath of pure nitrogen or any fluid that does not contain oxygen, down you go. And also, LNG is very cold. I've gotten I had a freeze burn on this finger one time, and I was making up a fitting, and I knew I was getting burned, but I had gloves on, and just I made up the fitting, and I took the gloves off. I looked, and it looked very strange. At first, it numbed, so it didn't really, but it felt like I knew I was getting a freeze burn, but I was stupid. It was early on in my career, and I didn't want to say anything, but eventually it started getting black. And I went to the doctor, and the doctor says, well, you're lucky you didn't get it all the way around the finger because then you would have had a real problem. But this should heal. And it took about 3 weeks for it to heal, but it was a significant burn. I know of only one person in our industry that's been killed by LNG, and that was where this was in Algeria, a valve burst, and the person was covered with LNG, and he was a fatality. And that's only by reading and hearsay. It's not by, oh, I knew the person. I didn't know the person. I didn't work in Algeria, etc. Its vapors are flammable. When you have the correct mixture of air and gas, and we'll talk about that correct mixture momentarily. Let's understand the combustion process. Combustion process occurs when you have a methane molecule, and I'm showing it right here, and I'm really showing 4 hydrogens and 1 carbon in the middle. That's your methane molecule, and it reacts with 2 oxygen molecules, O2. So this is an O2 and this is another O2. Reacts with 2 oxygen molecules to produce CO2, which is a gas, and it's a gas under our pressure and temperature, atmospheric pressure and temperature, and 2H2O, 2 water molecules. So it produces 2 water molecules. And it also produces heat. Now, that's a combustion of this one set of molecules. Now, if that heat is enough heat to get through to the next set of molecules, then they will reach their activation temperature and also combine, producing more heat and producing CO2 and H2O. Now, H2O is water vapor. You ever see when you start your car and it's cold outside, you see water dripping out your tailpipe? Well, that's liquid water that's condensed out of your combustion products. Now, you're not burning methane, but you're burning a long hydrocarbon chain in gasoline. Actually, many different long hydrocarbon chains mixture in gasoline. But at any rate, this is the process. Now, how do you stop this process from occurring? Either by removing the fuel, or by removing the oxygen, or by putting insulation between what just burned and what's going to burn, or what's intended to burn in the future. What kind of insulation can you put in here? Let's say I put a bunch of fuel molecules in here. Well, that will insulate this so that that heat never gets to the next set of combustible molecules. Let's say I put a lot of air molecules in here. Well, that acts as an insulation so that heat never gets here. Let's say I put a lot of nitrogen in here. It also acts as an insulator so that that heat never gets here. Now, this is a flame, and this is a flame propagation when the heat gets to the next set and it propagates. So there are cases where the flame will propagate, and there's cases when it won't. And when it won't propagate is when it's too lean. There's too many air molecules in the way that act as insulation. Or when it's too rich, there are too many fuel molecules in the way. Or when there's not enough oxygen, because then you have too much air molecules, air and fuel molecules in the way. So what happens if you're in a zone that's shown here in red? Well, then you'll get a significant burning taking place, and you'll get a propagation of that burning. So let's say I was in a room with 20% fuel and 80% air, and I strike a match. The flame that gets the air gas mixture that gets sucked into the flame may combust, but then the flame goes out. Why? Because the heat cannot transmit to the next set of molecules, because there's just too much fuel. I'm at 20% fuel. I'm way up here in the fuel range. Let's take a look at where I am. All the way up here in the fuel range. So I'm not going to have this occur. Now, if I happen to be in a 20% uh, fuel and 80% oxygen range, that's a whole different story. But I'm talking about normal atmospheric air. So this would be, and as I add fuel, why is this line curved? Not curved, but on an angle? Because as I add fuel, I'm diluting the air with natural gas. So really, when I'm up here at 5% gas in air, I'm really at about, looks like about 20% uh, oxygen and 5% gas. Well, that's going to give you, that's called 1 LEL. What is LEL? It's the same as LFL. LEL stands for lower explosive limit. LFL stands for lower flammable limit. They're used interchangeable within our industry. And what is this? This is the, oops, wrong mouse. This is the UEL, upper explosive limit. And for natural gas, that's roughly between 5% gas and air and 15% gas and air. That's typically what's called, maybe this is 15.5, but in our industry, we typically say between 5 and 15% gas and air. Now, let me tell you about hydrogen and acetylene. I only picked those two for a reason. Hydrogen and acetylene have very wide flammability limits. And the hydrogen is something like 4 to 75%. For acetylene, it's something like 4 to 84%. Really wide range. When I was a kid, I remember I was fascinated by welding. So I said, I'm going to learn to weld. So I went and got a whole bunch of lead acid batteries that were in the garage. Fortunately, they were half dead. And I hooked them up in parallel. I put a plate of steel on. I got a clothes hanger. And I said, I'm going to learn how to weld. And I'm starting to arc spark, stick, arc spark. One of the batteries blew up and I got a face full of acid from the battery. Fortunately, it was dilute, very weak acid because the battery was mostly dead. I went to run in the house and to wash it off, but I can't open my eyes, so I ran right into the brick wall. Eventually found my way down to the basement, washed it all off. I was all red in the face, red in the eyes, etc. But fortunately, no permanent damage. Uh, but that left a lasting impression on me. It was detonation of, and I say detonation because there's a very high flame speed associated with hydrogen. So it can very easily detonate. Maybe it deflagrated, but I certainly blew up that battery. Being it was in an enclosed space of the battery, I'd say it detonated. So hydrogen, I'm very cautious about. Acetylene, I had two welders working on a job, and they used to store their acetylene torch inside a metal cabinet. And there was a hole in the metal cabinet that fed the hose to the acetylene tank, which was in the back of the truck. It was an open back truck. They should have never stored the torch inside because what happened is they did their job. They shut the torch, put it down, closed the cabinet, never shut the acetylene tank off. And while the guy was grinding the pipe, spark got by the cabinet, blew the door off the cabinet, ripped the muscle out of one guy's arm, hit the other guy in the leg, ripped the muscle out of his leg, kept on going, put a dent in his metal door. And I visited them at home. They were permanently disabled. And it's just something that shouldn't have happened. But acetylene also prone to detonation, and it's prone to has a very, very wide flammability limit. And I say that only because, uh, in comparison to natural gas, it's a lot safer dealing with it. Your job as engineers is to ensure that combustible gas mixtures occur only where they're intended to occur. That's in the combustion chambers of boilers and furnaces. Talk about safety moment number 20. And here we're talking about um, tank design, and there are many different types of tank. Now, this is an LNG tank shown here, and in fact, I know this one because I used to work at this particular plant. A lot of plants I've worked at over the years, 53 years. You get to work a lot of places, especially the last 20, 21 years because I've been doing consulting for LNG around the world. And here's a breather tank on this location. So I'm going, and in fact, I know I was going to guess on this, but now I recognize that this is a tank that happens to have an annular space that's full of nitrogen, not nitrogen. Yeah, actually, it's nitrogen. I'm sorry. I'm saying not nitrogen. It's actually nitrogen within the annular space. Now, what's the annular space? Okay, the annular space is the space between these two tanks. The inner tank is on a typical LNG tank, the inner tank is an open cup made of 9% nickel steel or of certain alloys of aluminum. Now, it's not typical to find aluminum in larger size tanks because aluminum gets to be over 3 inches thick or near 3 inches thick, and it's really unmanageable. So they typically use 9% nickel steel on all of the large tanks. So typically you have an LNG tank that has an open top. So in other words, the gas can get out of here. And typically you have bog pressure in here, boil off gas. When I say bog, that means boil off gas, pressure in here between the inner tank and the outer tank. And so if you put a gauge here, you'd actually read your tank pressure. Now keep in mind, every gauge is a differential gauge. You may take a gauge out of the store and look at it and it says 600-pound gauge. You think that's a pressure gauge. It's a differential gauge. It happens to show 0 at atmospheric pressure. But reality is we're not living in a 0 pressure environment. The fact that I can blow air says we are living in a pressurized environment. So in this case, this is not showing this type of tank. This is showing most of the tanks that are in our existence today are this type of tank. This is what's called a single containment tank. The single containment is this cup, this 9% nickel cup. And the LNG will be from a high level to a low level, etc., up and down. Now, what's on top of this roof? This is a suspended roof. There's insulation on top of this roof. Typically, it's perlite. What's inside this annular space? This annular space may be 3.5 foot to 4 foot space. What's in here is you have initially a foot of perlite and the rest of it, a foot of fiberglass, and the rest of it will be perlite. Now, why is there fiberglass and perlite? Well, perlite will not compress. It's like sand. You just can't compress it. It's a very light powder, though. It's not as heavy as sand. It's a very light powder. I should say it's more like a very coarse flour, or maybe granules like salt, but much lighter. You can blow it away. It's a very light powdery substance, but it cannot compress. So the fiberglass can compress. Now, why would you want the fiberglass to compress? Here's why. When you cool down this tank, it shrinks about 6 inches in diameter. So you cool it down, the tank shrinks. If you ever want to service that tank, you have to warm it up. The tank will grow. Well, if you had only perlite in there, as the tank grows, it'll start crushing the wall. So you need to make sure that you put that inner tank would start crushing the wall. So you need to make sure that you put a layer of perlite, a layer of fiberglass in here. So let's say that fiberglass, when compressed, is 6 inches, and when it's uncompressed, it moves out, let's say to 9 inches. It was originally 1 foot thick, but there's a certain amount of compression due to perlite. And then as the tank shrinks, it moves when the perlite fills in. Then as the tank grows, it's got to compress, and the perlite compresses. That's a single containment tank. What happens if the tank gets breached? Well, that tank breaches. The outer tank is made of carbon steel. It's only there to hold the boil-off gas and the insulation in place. So the outer tank automatically fails. It's just not cryogenic material. The LNG is captured within this inner dike, and that dike will prevent liquid from running down the street and going into the sewer mains like it did in 1944. Then you have what's called a double containment tank, and that's where you bring this dike in really close. So you bring the dike in really close so that if you do have a breach of failure of this tank, it contains the liquid and allows the boil vapor to escape, but it contains the liquid, and you get significantly less boil off because you don't have all of the surface area that's heating up this LNG. Then you have what's called a full containment tank, and these are the most expensive types of tanks. If you had to look at price-wise, whoops, I did that wrong. Go back. There you go. If I had to look price-wise, these are the cheapest tanks, most popular, most common tanks. These are more expensive tanks, and these are the most expensive tanks. You want to get more expensive than this? Full containment tank if it's underground. Now, underground tanks are also full containment tanks. And what happens with a full containment tank? If you get a rupture of the inner tank, the outer tank holds not only the liquid, but the vapor as well. So a full containment tank could cost, I'll just use order of magnitudes. Let's say if this was $50 million, this might be, and I'm making up these numbers, so don't quote them. $100 million, this might be $150 million. Just grabbing numbers out of the sky. But I'm saying in that order of magnitude, where this might be 3 times the price of this, just a much more expensive tank. Now, tank pressures are something that very important. The tank pressure, we realize it's a differential pressure. Let's say the barometer changes, which the barometer does change. In this case, I say, okay, here's the barometer at 14.7 psi, absolute. That's absolute pressure barometer. And I'll check time. Okay, I got 18 minutes left. And here the barometer is 12.8, which is the lowest barometer that's been measured. And that was measured at the eye of a hurricane. Here's on top of, this is in Siberia, the highest pressure ever recorded. And that's 15.7. And my differential pressure here, which you'd, as the operator, be reading, is continuously 1.3 psi absolute. Now, that assumes that you maintain that pressure. But in order to maintain the pressure, you have to go from here to here. You have to suck out a tremendous amount of boil off to get you down to 14.1 psi. And here you have to let a lot of pressure build up in here to get this up to 1700 I'm sorry, 17 psi absolute. Now, how does that build up? Heat leak into the tank. That's how it builds up. Or if you get too low a pressure in here, you're going to get your cover gas is going to kick in. So in order to get this this pressure up higher, you have to remove no boil off, let the pressure build up slowly. So you have to always be looking at what your barometer is for tomorrow. Today's barometer is today, but you look at tomorrow's barometer, so you take action today to anticipate the barometer. In summary, your job is to anticipate the barometer changes and to adjust your bog removal amounts accordingly. If a hurricane is coming in tomorrow, then today you start removing your boil off to bring the tank pressure down. If you don't do that, tomorrow when your low pressure front comes in, you blow the relief valves. Undesirable. Failing to preempt barometer changes can cause hazardous conditions, as well as result in costly venting of bog. Keep in mind, bog, when it comes out of a tank, is it heavier or lighter than air? Well, it's heavier than air. Why? Because and then you say natural gas, it's just natural gas, which is lighter than air, not at minus 256 degrees. It's boil-off gas, which is very cold, makes it very dense. Boil-off gas is heavier than air until it gets to be around minus 150 degrees as it warms up. Then it gets to be buoyant. When it gets to be atmospheric temperature, well, then it's about 0.6 times the density of air. So you have all of these issues that you have to deal with, knowing that boil-off gas is more dense than air and therefore will hug the ground. Safety moment number 21. Frost heave. What is frost heave? Underneath your tank, and it depends on the type of tank you have. There are some tanks that are held up by piles, and there's an air gap between the tank and the ground. You don't have to worry about frost heave there because the tank has the air flowing through, and typically it's about 18 inches to 2 feet in distance between ground level and the tank. So you got a good air movement in there, and you typically have it fenced with a chain link fence that you don't end up having animals habitate underneath your tanks. And those tanks that are on piles do not need to have foundation heating. However, if your tank is sitting on the ground, think about how your tank is constructed. You have a 9% nickel steel, a little bit of sand, and you got not fiberglass, foam glass insulation. Then you have your outer tank bottom. Then you have more sand, and through that sand, you have heating conduits. Why do you have heating conduits? Because you're going to be continuously pulling heat out from the ground into your LNG. Heat always transfers from the hotter location to your colder location, regardless of how much insulation you put. So your LNG sitting there at minus 256 degrees Fahrenheit, the ground is always going to be transferring heat to that LNG unless you put something in there that pumps heat in. So you put conduits in there and you run electric wires through there and you heat that ground that's underneath your LNG tank. It almost sounds counterintuitive because there's that heat going into your tank, but you need to make sure that the ground underneath does not freeze. If the ground underneath freezes, you get ice lenses forming, which push up, push up, push up, and then can damage your tank. I went to one plant where uh, and I always question, I always take a look at that. One of the things I always order to look at that foundation heating system. Why does a foundation heating system fail? It fails because the wires get hot, and when you turn on and they stretch, and then they get cold, and they shut off, and they turn on and they cold. And as it does that, the wires chafe along the edges of the conduit. Eventually, the insulation wears out, and they short out, zap, you have a problem. What is typically provided for heating? Typically, it's three number 12 wires that are run on three-phase system, 480 three-phase voltage. It doesn't have to be that, but that's what I've seen the most times. Now, you can improve that heating system by instead of making them on, off, having it modulate so that it gives just enough voltage to provide just enough amperage to keep the bottom at always with the wires not going cold, hot, but staying at a fixed, relatively fixed temperature to hold the bottom temperature of the tank at whatever that temperature is. Where do you test the temperature at the bottom of your tank? You have separate conduits that are going across, and you have different temperature sensors in those separate conduits so that you're measuring not the temperature inside the heating conduit, but the temperature of the sand that's underneath the tank. We talked about this, the maintenance of heating systems. Every so often, if you have one that's operating well, you replace the wiring or at least monitor the wiring, can check it for its condition. Let's say you pull one set out and say the wiring looks pretty good, the insulation's good, and that's hopefully representative of the rest of the conduits. But sometimes this wiring can short out. And there have been cases where it's short out and it's welded to the conduit. Now you try to pull it out and it breaks, and that weld spot is stuck underneath, and you cannot stick additional wiring through. That is a problem. So what you have to do is take the conduits next to it and make sure they have additional heat so that you're able to count counter for that missing conduit. Also, another way to handle it is you send in a heat tracing wire in both directions to that point to where it stopped, and you heat in that way so that to the extent that you can replace that heat that is needed in that area. In summary, for this event, your job is to monitor the system, to coordinate with management, engineering, and maintenance and other stakeholders on the status of your system. If you find out that the operators are not keeping the heat tracing system on as or operating appropriately, you have to certainly take action because you can end up with a damaged tank. And that's the most expensive part of your plant. Now, most of the plants that are in operation in the United States today were built between the 1960s and the 1980s. So these are all tanks that we're talking about more than 50 years old. They're probably grandfathered, which means you would not be able to replace them today if you had to. Very serious condition. Safety moment number 22. One man died and 5 men were injured. And this is the one that I told you about when my boss was killed. In this case, what was failed? Lack of lockout tagout. Job was well planned, except for lockout tagout. It was well executed, except for lockout tagout. And the end result, one person died, 5 people were overcome by nitrogen gas mixture, mostly nitrogen initially, but then gas followed. Let me explain what happened. This was a 48-inch diameter gas main, large diameter gas main. The main was shut down properly with all the proper valves closed, etc., but without lockout and tagout. His 48-inch main was maintained at 6 inches of water column pressure, roughly 1/4 of a psi. And stoppers and bags and stoppers were put in here. Bags and stoppers were put in here at this location with a vent hole in between. Being this was 48-inch main, the size of the stopper hole, 6-inch diameter threaded stopper hole. I used to be familiar with the types of machines that were used to drill and tap those holes. At any rate, this was a cast iron main. At some parts, it was an inch and a quarter thick. That's how big this main was. In fact, to cut this out, we had to use plasma arc torches to actually cut this. How do you cut a 48-inch diameter, inch and a quarter thick piece of steel? Now, in some areas, it was an inch and a quarter. It was more inch and a quarter at inch and a half at the fittings itself. Don't forget, these are castings from late 1800s to early 1900s. So they got to the point in the job where they were pulling this section of main out. There were men in the opening. Somebody walked out of this compressor building, saw that a 2-inch valve, a lousy 2-inch valve, was closed on the odorant system. So, oh, that valve's supposed to be open. It's always open. So he opened that valve, which brought 60-pound gas into this line. Now, there may have been other places where it was hooked up where that 60-pound gas dissipated, but it was enough pressure to kick these stoppers. And the stoppers are only rated for about 8 inches of water column. So let's say they got up to 10 inches of water column and kicked, which means that they failed. And that gas, this main was full of nitrogen, started pushing into this opening and kicked this stopper that was over here. And the nitrogen, can you smell nitrogen? No. Can you smell boil off? No. So in this case, it was nitrogen blowing into this opening. Nobody smelled it. Guys started collapsing. Other men went into the opening. Now, this is when I interviewed the men, what they said. They pulled their shirt over their face. They realized these guys were being asphyxiated. They pulled their shirt over their face and dove into the opening. And as soon as they got in, boom, they collapsed. Why? Shirt over your face does nothing for lack of oxygen. If you were dealing with, let's say, an environment that had to deal with powdered, poisonous powder in the air or particles in the air, yeah, maybe a mask might help you, but certainly not in a lack of oxygen case. It does nothing for you. But they didn't know this. Pulled their shirt over there now and went in and they collapsed. So now there's 5 guys in the opening. My boss, who was at this location, gets in his car, rides to here, has with him a Scott pack. A Scott pack is a air breathing apparatus. Jumps out of the car. Scott pack hits the ground, looks in the open, sees the men, jumps in. He collapses. He collapses with his face closer to this exiting gas, and that's when I called his house and found out there was what was said on the television was an explosion. It was a gas incident. There was no explosion that took place. And unfortunately, of the 5 people, 6 people in total, he was not resuscitated and he passed away on this job. What happened? Lack of lockout tag out. That's what happened. Exceedingly important. Lockout tag out is one of the things. When I go to a fire watch, I ask them, do you know how to use that fire extinguisher? Explain it to me. You always got to be ready to go after all of these things. Lockout tag out procedures should be incorporated into every procedure where it's appropriate. Besides lockout tag out procedures, continuous air quality monitoring for any locations where nitrogen or gas could become an issue. Anytime you go into a confined space, oxygen monitors must be used. Training on responding to a lack of oxygen instance is very important. Conclusion, lockout tagout must be used on all jobs where valve positions must be ensured. Where risk of asphyxiation exists, continuously monitoring and alarming equipment should be used. Where risk of asphyxiation exists, harnesses should be used on personnel to pull them out of the opening if necessary. Self-contained breathing apparatus should be available to personnel. All gas operating personnel require training on the effects of lack of oxygen. One of the effects of lack of oxygen, let's say if you're in a marginal area of lack of oxygen, 19.5% is the OSHA limit. You cannot go into a place with less than 19.5%. But at 16% oxygen, everything, you get very fatigued and your mental cognitive ability gets impaired. So you make wrong decisions. Very critical that that does not happen. Here's another safety moment. This is where the 2 men were killed. Check time. We still have about 4 minutes. 2 men died and others were injured. What happened was procedures were not followed. It was typical when you had a gas main, put a new gas main installed, to put a cap on it and pressure test it. So it's typical to put a cap on it, pressure test it to 100 psi. And this crew was used to operating with or putting in 6-inch diameter gas mains, which has a very minimal amount of force on it. Think of it this way: 6-inch diameter, 3 squared, that's 9 times 3. 9 times 3 is 27 square inches times 100 psi. That's 2,700 pounds force on the cap. Not a heck of a lot of force. Get up to 24 inches. Now it's 12 square. That's 144 times pi, which is roughly 3. So now you're talking about 450 square inches times 100 psi. You're talking about like 24,000 pounds of force. The welders were supposed to put 7 inches of weld material on these straps. What happened over the years, they got lazier and lazier, and I shouldn't maybe say it, I don't want to accuse them of being lazy, but they didn't realize the importance of all this weld material. And before you knew it, instead of going all the way around the straps, they went only on 2 sides of the straps. Over a period of time, then it became, instead of 3 passes, 2 passes, then it became 1 pass. Eventually, they were almost tack welding these on. Maybe not tack welding, but better than tack welding, but they were not putting enough weld material. Cap blew off, and the 2 people standing on top of the plates were killed. Now, I said to you before, I just said 24-inch, 45,000 pounds of force. Whoops, go back one. 6-inch, 2,700. That was approximately, I said 2,700, 2,800 pounds of force. And that's just because I used pi, I used 3 instead of 3.1214. Take a look at how dramatically the pressure changes by the diameter. It's not linear, it's exponential change. Conclusions: accidents are avoidable. The welders had followed procedures, this accident would not have happened. After that, we eliminated the use of all caps, dresser caps, and we welded everything. We should expect cold weather every year. The engineer reports to the chief engineer. I was the chief engineer. We had 274 customers lost gas service last night. And I said, why? He says, well, it was cold out. I said, that's not an acceptable excuse. It's cold every year. We design for the coldest design hour. It is an unacceptable excuse to lose customers because it's cold out. We should engineer that out of our system. Yeah, the lessons learned. There are 5 events that I spoke about, and one of them is that an operator got up and an engineer got up and raised my hand, asked the question, have we identified all the low pressure areas? And he said, yes, we have. And then I said, oh, I said, what I asked is, have we not identified, have we accounted for all the low pressure areas? He said, yes, we have. I felt good. We said, well, afterwards I asked him, what does accounted for mean? He says, it means we know where they are. That's not acceptable. I had to contact everyone that was at that meeting, tell them we have low pressure areas that have to be repaired. So that concludes the presentation, and I think we're at the 120-minute mark, but I had forgot to set my timer at the beginning. So please let me know, Hisham, if we're at the 120-minute mark.
All good.
Are we there? I believe so.
All good. You're fine.
Okay, very good. Thank you, Hassan. And thank you for choosing N-Site for your continuing education course. N-Site is a premier provider of continuing education courses, and I encourage you to take more of them. Have a great day. Thank you.
See the note in chat on how to get the certificate. And if you have any question, please type them. We'll
And if
see.
you have any questions, please ask. Anybody out there? I don't hear any questions. About getting your certificate, you will be receiving an exam. Oh, thank you too. I appreciate that, Eric. There's a lot of more information I could have given if time permitted. Diane, thank you. I wish I would have. This was a really an abridged version of an 8-hour course. Very abridged. Thank you, Hisham. I'm going to leave the meeting at this point. Have a great day.